that it's a pretty important rule that shows up a lot. And so to start off, so this is shared in your OneNote. I'm not really going to write anything on this slide, but these are 4, I guess really 8 functions that show you ones where we would not use a chain rule, and then some where either the chain rule can help us or they're really just impossible to do without the chain rule. So like in that left-hand column, those are all functions we would know how to do the derivative of. Like that first one, we see it's just a linear function. We know that its derivative is just going to be 3. This second one, we know that we could rewrite it first and have something like 1/2 of x squared plus 3, and that will be another easy derivative to take using the power rule. 2 cosecant of x, constant multiple, and trig rule. And then we also know how to do problems like where we're adding multiple terms. We just take the derivative of each part. In that other column, I have some where the chain rule would help us. These 2 trig ones you actually cannot do unless you have the chain rule. So for these last 2, the chain rule is actually required, and we'll see why in a second. But we have the cosecant of 2x, that would require the chain rule. Also this last one where I have the tangent of x plus 4x squared, that one would also require the chain rule. These first 2 you actually can do without the chain rule. Like for example, the second one you would use the quotient rule. But personally, and we'll kind of see, I think the chain rule is easier for this one. This first one is definitely one I would want to use the chain rule for, because either you're going to do like a, just going to make up a phrase, a super extended product rule, or maybe you FOIL this out your life away. It's the 10th power, so yeah, you'll be FOILing forever. This one, the chain rule is going to make it much easier when we have it. So what we're going to talk about today is when we know we have to use a chain rule and ways we know the chain rule will make it easier for us, how this chain rule works, and then do a bunch of problems. I do have today's notes taking 2 days, just because I do have a lot of examples, so whatever we don't get done today, we will finish up with tomorrow, and then we'll regroup next week and kind of see where we're at, but only one more homework assignment really assigned today. So when do we need the chain rule? I think about us needing to use a chain rule when I have an inside function or an outside function. And when I do the chain rule, I kind of think of like a blow pop or like a Tootsie Roll Pop. If you're sitting in class with me, I'd probably give you one to look at. But that's basically what I think of with the chain rule. Some teachers also explain it with like, I don't know, like those Russian nesting dolls where you open it up and there's another one inside. You keep opening it up and there's dolls inside of each other. And then some teachers like describe it as like a donut and donut hole. Mainly the thing we're going to be thinking about is we have like an outside function and inside function or inside functions. And we do also will think about is there's like a certain order we have to go in. For example, if I give you a blow pop, before you can even enjoy it, you have to take the wrapper off. So like for us, you're going to have to like do something with the outside function first. Then you can get to the hard candy part. And then after you get through the hard candy, then you could get to the gum in the very center. So you kind of have to work your way from the outside to the inside. And that's basically what I think about when I'm doing the chain rule. I think a lot in terms of like the inside portion and the outside portion. So these are the 4 functions we've looked at on that right-hand side. And I want to right now, before we even find the derivative, I want to talk about just like what will be the inside and the outside portion of these functions. I think inside is a little bit more obvious. Like if you're looking at this first problem, I think it's easy to see that the inside function is this 3x minus 4. And that is inside of what's on the outside function, which is basically something to the 10th power. So one way to kind of think about it, the outside function is something to the 10th power. And whatever that something is representing our inside function. I'm just going to use the variable u to kind of represent inside portion of the function. This second one, could use the quotient rule. But if I rewrite it, it actually becomes one that's pretty easy to use the chain rule for. Similar to the one above it, we have this inside portion, and then we also have the outside function. So if I were to describe the second one, I would say, hey, this looks like something that's 2 times something to the negative first power, and that inside something is this x squared plus 6. I do think the trig ones are a little bit easier to see. So if I'm looking at the trig, you can kind of see, oh, this looks like the cosine of something, with the inside being 2x. So we have the outside and the inside. Same thing with the tangent. In simpler form, this is the tangent of something, with the inside being the x plus 4x squared. So one of the first things that comes to using the chain rule is being able to correctly identify what is the inside and what is the outside function before you even take the derivative. That's also kind of true, like, you know you're using the chain rule if you have a function inside of another function and can think about it in this way. So first I do want to tell you kind of like how the chain rule works. And so I have the Leibniz and the Lagrangian notation up here. The Lagrangian notation, that's the one where you use the prime notation. I think it's a little bit easier to write out the chain rule. So one way to think about the chain rule is you're taking the derivative, and I have this f of g of x. We know that another way to write that is using function composition. So sometimes this is written as f of g of x, like that, where we have like the little open circle to show function composition. And when we take the derivative using function composition, this is the chain rule. It says that we're going to take the derivative of the outside function. The inside function stays the same. And then you multiply it times the derivative of what that inside function is. That's where it gets its name chain rule, because you're basically linking together the different parts through multiplication. This is also why I describe the chain rule as kind of like, think about like a lollipop. So you first have to take the wrapper off. So that's me taking the derivative of the outside. We still haven't tasted the inside, but then once the wrapper is off, then we can taste the piece of candy. In the Leibniz notation, the way it's usually written looks a little bit weird, but you first take the derivative of the outside, so we're going to call that like dy du, and you're going to multiply that by the derivative of the inside with respect to x, and you can kind of see that those du's cancel out. I know we don't normally think about fractions, but this is how we write the statement using Leibniz notation, where u is representing the inside function. So we're going to go back and look at those 4 examples and just kind of take the derivative of them using the chain rule. If you printed out that formula sheet, or if you're just trying to keep it filled in, I did copy it over here. So this is the chain rule on the formula sheet handout, either at the top of OneNote or some of you did print it out. So when you take the derivative using the chain rule, again, this is when you have a function outside and another function on the inside. I'm just rewriting the rule again. You take the derivative of the outside, inside stays the same, and then multiply it by the derivative of the inside. So an easy example of this to look at is if I have the sine of x to the 7th. So how we can interpret this is, hey, this looks like something to the 7th power with the inside being sine of x. And so when I take the derivative, you do the derivative of the outside first. So the derivative of the outside is the power rule. 7 comes down in front. The new exponent is a 6. By the chain rule, though, the inside stayed the same, but then you took the derivative of the inside, so multiply. The derivative of sine is cosine. So that's the basic idea behind the chain rule. Any questions about the notation or the process before we go back and do those 4 problems as an example? All right, so let's go ahead and look at these examples. So here are the first 2. I'll make that a little bit bigger for me. So the polynomial ones, again, are pretty easy. Sometimes you can rewrite them and do them first. So if I'm looking at this one again, you kind of identify what's the outside function and the inside. We had already said before this looks like saying something to the 10th power, where the inside is this 3x minus 4. You wouldn't have to write that down, like we can visually look and see that. I'm just mainly doing that for the sake of notes. So again, taking the derivative of this, power rule first, 10 comes down in front, the new exponent is a 9. Haven't touched the inside yet, but once I take the derivative of the outside, I can multiply this by the derivative of the inside, which is just 3. The derivative of 3x is 3. 4 is a constant, so it goes away. If I'm simplifying this, please don't distribute exponents across parentheses. Also don't distribute numbers across parentheses when there's an exponent there. So really the only way to simplify this is going to be 30, 3x minus 4 to the 9th. Questions on that one? All right, so the other one is one that you could have used the quotient rule for first. Some people really love the quotient rule. I think it takes a little bit too long to do. So if I'm going to use the chain rule, again, we can rewrite it, and I can bring that whole denominator up with a -1 exponent. So now I can think of this as really just 2 times something to the -1st power. So when I'm taking the derivative, that -1 comes down in front, so I have -2. The new exponent, -1 minus 1, gives me -2. Inside stays the same, and then I can multiply it by the derivative of the inside. If I'm simplifying this, I have -2 times 2x, so that gives me -4x all over. I can send this back down to the denominator with a positive exponent. Again, you could have used the quotient rule if you're using the quotient rule to do this problem. So we had, for my derivative, I have low d high less high d low. Draw my line, and down below, the bottom squared will go, and simplifying this, we still end up with -4x over x squared plus 6 squared. So we get the same answer. Like, I guess it's up to you if you figure out which one's the easiest for you. I will say, as we progress through calculus, I think the chain rule is often easier than the quotient rule, especially if that numerator had not been a number and maybe had something with a variable in it. Questions on that? All right, go ahead and try the 2 trig ones on your own for me then. So again, those are your functions, and I want us to find the derivative of them. And you just want to think about taking the derivative of the outside, carrying the inside across, and then multiplying by the derivative of the inside. And if you're looking at these, I actually think the tangent one is probably easier and less likely for you to make a mistake on. Because I'm actually going to do the tangent one first, I think. So if I'm taking the derivative of this one, we have tangent is on the outside, this x plus 4x squared is on the inside. Using the chain rule, the derivative of tangent is secant squared of x, but this has more than x on the inside. The inside, though, carries across. If I write it down exactly correct, x plus 4x squared. And then we multiply it by the derivative of the inside. And the derivative of the inside would just be 1 plus Questions on that one? All right, and then going back to this one, I think this one's tricky because the derivative of cosecant is kind of weird. I'll just kind of go off to the side to remind you, if you're taking just the derivative of cosecant of x, its derivative is the negative product of cosecant and cotangent. And notice how the x is repeated twice in that. You have to kind of do the same thing with the chain rule. So the derivative of the outside is negative cosecant cotangent. That inside is going to be carried across to both of them. And then you multiply by the derivative of the inside, and the derivative of the inside is 2. So your derivative for this one becomes negative 2 cosecant of 2x cotangent of 2x. Lots of people, I often see mistakes when they do the derivative of cosecant and secant with the chain rule because they don't carry that inside across to both of the factors, because it is a weird derivative rule where the inside kind of happens twice. Questions on that before we just look at some more examples for the rest of the notes? All right. Other common mistakes. People not interpreting how the exponents work when you're looking at these problems. So I have two questions here. I have y is equal to the sine of x squared and y is equal to the sine squared of x. So these look the same, but they actually have very different derivatives because they have different outside functions. If you're looking at this first one on the left, y is equal to sine of x squared, what's technically the outside function for that one?
Sine.
Sine.
Let me just sign.
A lot of people think it's a little bit more clear if they write it as this is the sine of x squared. Versus if you're looking at the second one, y is equal to the sine squared of x. What's technically the outside function when I say sine squared of x?
Sine squared.
The squared is the part that's on the outside, yes. So we can think of this as y is equal to, this is something squared. What's being squared is sine. They won't be written with those parentheses there, so we do have to make sure we just understand the math notation. So when I go to take the derivative of them, so for this first one, the derivative of sine is cosine. Inside stays the same, then times the derivative of the inside. Compared to the second one, y prime is going to be, the outside function is something squared. The inside stays exactly the same, and then multiply by the derivative of the inside. And of course, that second one looks a little bit nicer since that's just sine to the first power, as writing it as 2 sine of x cosine of x. So we can see that they are very different derivatives because they are naturally very different functions depending on what's on the outside and what's on the inside. Questions or comments? All right. Say it again.
For the 2 sine x cosine of x, I might be wrong, but isn't that a trig identity?
It is, if you wanted to simplify it. Do you remember which one it is?
Is it? Oh, it's sine of 2x.
Yeah, so this technically is the same thing as the sine of 2x if you happen to remember your double angle identities from pre-calc, which Alexander does. But leaving it as 2 sine of x cosine of x would also be fine. And let's do, I'm gonna try to do at least one more, or really 2 more. I have 2 on the slides. So sometimes we have examples where we have repeated chain rules, hence my little picture of 2 chains, which I was a big fan of in college, which might be dating myself. I don't know if people still listen to 2 chains, but college Daniel definitely did. The chain rule is called the chain rule because you can keep linking things together. So like every time you can have multiple like insides, you just want to make sure you kind of think about you first have to unwrap it, then you get to the hard candy, and then you get to the gum. And then we have this chain rule because we know that every time we take the derivative of a new inside, we have to end up multiplying. So I have these two on here. Both of these are examples that have you do the chain rule multiple times in a single problem. But you do have to make sure you have the order correct. So let's look at this first one. I have the tangent of pi x squared. What is the very outside function when I see the tangent of pi x squared? What's on the outside of that one on the left?
Tangent.
Just
Tangent. So we're going to look at the tangent first. What is inside the tangent? What's going to be the next function inside of tangent? Pi x or something squared. Something squared. So that's going to be on the next inside. And then we have the very inside, pi of x. So when we think about unwrapping this, we first are going to do the derivative of tangent, leaving the inside the same, then the derivative of something squared, leaving the inside the same, then the derivative of pi times x, and then we're done. So I'm going to take the derivative, I'm going to try to color code it. So I have y prime. The outmost function is tangent. The derivative of tangent is secant squared. But I want to leave the inside the same. So then the one on the next side is something squared. So I'm going to multiply by its derivative. This is the power rule. 2 comes down in front. The new exponent is a 1. What's still on the inside? Pi times x. Now I can take the derivative of the very inside. The derivative of pi times x. Pi is just a coefficient on a linear term. So the derivative of pi times x is just pi. You can leave it like that. We can clean it up a bit though. And I see I have a 2 times an x and times 2 pi's. And that's times secant squared pi x squared. And you can see we kind of just did this unwrapping motion where we left the inside the same, and you just kept multiplying by the derivative of the inside.
Wait, how do you get the steps 1, 2, 3
You just have to think, I guess, kind of think about order of operations. You want to think about what's on the outside and then kind of work your way on the inside. It might help if I rewrote that first one. We can think of this is it was the tangent of something squared, and what was that something? It was this pi times x. So we had to kind of think about the order of operations of working our way from the outside to the inside.
So,
Wait, for the page before that, for the sine x squared, if the x was in parentheses, would you have to do the same steps as the repeated chain rule?
Which one am I looking at again? I'm sorry.
The left one?
The left one. So I don't know what you mean by x in parentheses. If I wrote it like this.
Yeah, so what's the difference between that and the one we just did?
So sine with the x in parentheses is just the same. If you think about it, I don't know if this will help or not, but that's just an x on the very inside with a coefficient of 1. So you're kind of always doing the chain rule if you think about it. I don't know if this is about to confuse people, but what's the derivative of x? The derivative of x is just 1. So technically we've always done the chain rule, we just haven't shown it because the inside's derivative is just 1. You asked how this one compares to when we just did. This is the sine of just x, whereas this one that we did, we don't have just x that we're taking a
So
trig
it's
of.
multiple things
Pi
on the-
times x. So yeah, x is multiplied by something. So we knew it was something more than just an independent variable in there, giving us our clue that we have to use the chain rule.
Okay.
Kind of if I just said something like the tangent of x versus the tangent of 2x. That coefficient tells us that we are having to use the chain rule at some point. Anna, you have your hand up. What's your question?
I'm just confused why you
did secant squared of pi of x squared if the squared was its own step? Like, why is it pi of x squared?
Trying to think what you mean. Like, you're talking about, I'm about to highlight it in purple. This part right here.
Yeah, like why wouldn't it just be pi of x? Like why is that squared?
Because that is the inside of tangent. So we had to carry the inside across.
So then why is it a different step?
Why is it a different step? Because by the chain rule, you have to keep, like, that you can't touch the inside. Like, you take the derivative of the outside, the inside has to come down exactly as it was, and then you multiply by the derivative of that inside. So let's try the second one. I think let's see how the second one goes.
Mr. Brown.
Let's try the second one, then we'll continue. I think
No,
I'm going to answer some questions with the second one.
I was just thinking, couldn't you just square the pi and x? Because pi is just a number.
Yes, you could have written that as pi squared of x squared, but then you wouldn't have a double chain rule and it would mess up my notes.
Oh, okay. I
It's
was
the
just
short answer.
confused. Okay.
Yes, as long as you can do good algebra, then it's fine.
Got you.
So let's try the second one, and I think that might help us see the steps. So this one, I just kind of rearranged it so it's a completely different function. If I were just to rewrite it so I can clearly see like what's on the outside, the inside, and the very inside, what would you consider to be the very outside function of this one?
The squared.
The
The
squared.
squared. So you can think of this as the tangent of, I'm going to add some parentheses here to make it a little more clear, of pi x squared. So when I go to take the derivative of this one, we'll see if this helps. We can think of this as basically, I'm taking the derivative of something squared. Well, what's the derivative of something squared? It would just be 2u to the first power. So when I do that first step, the 2 comes down in front, the new exponent's a 1, and then I had the u there, the inside, we're not touching. But then we see that we do need to use the chain rule here. So I do need to multiply this by the derivative of u, the derivative of the inside. The derivative of the inside is basically secant, nope, that is the answer. That might be confusing people. The inside is like tangent of something. So I'm just going to think of this as like tangent of something. We know that the derivative of tangent is secant squared, but we have to do our chain rule here. So I have the derivative of tangent, which is secant squared. Inside stays the same. Well, that inside is pi times x. That's not just an x. So I need to take the derivative of pi times x, which is just pi. So this would be the derivative of that second one. I don't know if that was more confusing or less confusing. We'll see in a second, I guess. Questions on that one?
In my mind, that second one makes more sense than the first one.
Yeah, I think that was a little bit easier to understand because it's when you're talking about inside and outside, I think it's easiest to think about having like a power rule on the very outside being easiest. So I have another slide, but I'm going to go make up another one just to make sure like we're all on the same page. Go ahead, Anna.
Where'd you get secant squared of pi x from?
The derivative of the first inside, the derivative of tangent is secant squared. And then we carry it across the inside. Let me do another one real fast. We're going to take the derivative of the cosine cubed of 5x. So I'm taking the derivative of cosine cubed of 5x. So we want to work our way from the outside to the inside. a way to think about this one is this is the cosine of 5x cubed. So we're going to work our way from the outside to the inside. So when I do my derivative, the outside function is something cubed. The derivative of something cubed would be a power rule. 3 comes down in front. The new exponent is a 2. This inside carries through, so then I have the cosine of 5x. The chain rule states when there's more than just x on the inside, I need to multiply by the derivative of that inside. The derivative of cosine is negative sine, but again, that 5x is being pulled across. What's the derivative of 5? The 5x, the derivative of 5x is 5. If I were to clean this one up, again, because it's all just being multiplied, I have negative 15x times the cosine squared of 5x times the sine of 5x. So I don't know if that one helps a little bit easier to see me like working from the outside to the in. I think that other one might be confusing because the derivative of tangent is secant squared, so it looks like we're adding exponents. I think that might help you see the process a little bit better. Maybe. Questions?
Wait, where'd the x in front of the negative 15 come from?
I don't know. It's not there. It's just negative 15. Thanks, Matthew. Any questions on that now that I fixed it? All right, so I'm going to stop notes there because the last 2 examples I have are not the shortest examples. So what we're going to finish up with tomorrow, just so you can kind of see, I'm going to have an example where we are going to be combining rules. So sometimes you have the product rule and the chain rule at the same time. Sometimes you have the quotient rule and the product rule at the same time. And then we'll just also remind ourselves about actually finding second derivatives. And I'll start off with a warm-up tomorrow. So that's where I'm going to kind of stop today's notes. Your homework is on the calendar. So you can begin homework 5. It's from the textbook, but it is scanned in and copied into OneNote. You can also, like homework 7 will be assigned officially eventually, but I actually have nothing to teach you about homework 7. You can do it if you want to work ahead, or you can also begin working on quiz corrections as well. So we'll finish up the chain rule tomorrow. Monday, we're going to learn about exponential and log derivative rules, which are just going to be, they're pretty easy, to be honest. I know that's the calculus teacher saying that, but they're pretty straightforward. And then your test is actually next week, so welcome to BC, where we fly through material. So yeah, I'm going to go ahead and end this meeting. Like if you need to go, then go ahead and go. If you want to hang back and ask any more clarifying questions, and of course, feel free to do that as well. Yes, Anna.
I'm gonna do the iReady, but like what happens if I don't do it? Like